Hello everyone, welcome back. So in this video, we are going to understand a very important question from the Leetcode is count square submatrices with all ones. Okay, so the question is saying that we have given a array matrix m cross n of ones and zeros, where we have to return how many square submatrices have all ones. As you can see in this problem statement, right? So here we need to find uh, the number of square submatrices that contains only ones, right? As you can see here. Okay, and this is a binary matrix, you can say, because it contains 0 and 1. Okay, so a square matrix have equal rows and columns, such as let me tell you how. So I'm saying like I was saying the matrix, right? That matrix we have, right? And a square matrix uh, should have equal rows and columns, right? And those, all the number of sub-required matrix we will return, right? We have to count those and we have to return. Means if you talk about the square matrix that have equal rows and column, means we can get how? We can get by 1 cross 1, or you can say 2 cross 2, or 3 cross 3, and so on, right? Very first, let's suppose we talk about the 1 cross 1 submatrices from here, right? Where each cell have one contributes directly to the count, right? So can we say 1 cross 1 matrix is nothing but very only one element, right? So for a matrix of size 1 cross 1, exactly one submatrix is possible, right? Now think about 2 cross 2, 2 cross 2, right? So for 2 cross 2 matrix of size 2 into 2, right? Exactly how many submatrices are possible? 2 submatrices are possible, right? Let's suppose how. If we write 1 1 1 1, right? So now this is nothing but 2 cross 2, right? So exactly here 2 submatrices are possible, that ending at the bottom right corner and here. How? Wait for some minute. Give me a second. Okay, so let's suppose for these 2 cross 2 matrix, right? And we have I and j both sides. Let's suppose this is I and this is j, right? We can say that. So each cell at I and j, let's suppose this and this, right, must be 1. Means if this is 0, this is 1, this is 0, this is 1, right? So at here, let's suppose that cell that contains E should be 1 1. So all the cells are containing 1 1, right? So the cell value, let's suppose for this case, okay, can I say I minus 1 and j, right? And there will be if this is, so let's call it, I did little wrong here, I should write I and j, okay, like this. So the possibility that, let's suppose we have I minus 1 and j. This is for the cell that is having above, right? Then we'll say for the left I and j minus 1, right? Then we'll say for the diagonal case I minus 1 and j minus 1, right? So this all should be uh, what you call, for particular this cell, this is the above cell, this is the corner cell, and this is the I minus 1 j minus no, this is the this cell, okay, left cell, we can say left, this is left, right, and this is above, and this is your diagonal, right? And we can get from here, means this is for your uh, above cell, this is your left cell, and this is your diagonal cell, okay? So if we want to write this into let's suppose we exactly want 1 0, and we can stop the submatrix from the beginning. How we can represent this? Let's suppose if we can represent 1 1 1 and 0, if we can represent 0 1 1 1, right? Then 1 1 1 0. So exactly 1 0 can stop the submatrix, right, from beginning on a all one matrix, we can say, right? So this is the possibility. Similarly, when we talk about the square matrix, right, 3 cross 3, so there will be a 2 cross 2 matrix that is formed by its neighbor, right? Let's suppose for, we'll say I minus 1, j minus 1, then there will be I minus 1, j, and I and j minus 1, right? These should be, must be valid, like we have seen for this case, right? For the 2 cross 2 cells. Let's understand how that will work. Okay, very first, let's suppose we have a matrix I'm talking about, okay, where I'll just, for example, if anything we have, right, we can say this is one, this is one, this is one, right? So we can form like this, like we will check the minimum of above, left and diagonal, it's never, right? Similarly, if we have a 3 cross 3 matrix that we are talking about, okay, let's call it 3 cross 3. Okay, very first, let's suppose this is 1 1 1 1 1 1. Okay, I have not taken one more. I clean it again. Let me go with this one. Okay, so let's suppose I'm going to create a 3 cross 3. Okay, we can take like this. Okay, 1 2. Okay, now think we have 1 1 1 1 2 2 1 2 2. Can we say that? So when we talk about the diagonal for this case, right, I'm talking about the above, diagonal, and its neighbor. Similarly, for this case, it's a above, diagonal, and neighbor. Again, for this one, neighbor, diagonal, and recall uh, above, right? We can say this is your above. Okay, and for this, similarly, this is diagonal and this things. Okay, so we have checked the minimum of above, left, and diagonal. So we will construct the larger submatrix that is relies on the a smaller valued one, as we can see, right? So this is a way we can say that we will find the what you call square matrix submatrices, and then we'll count that and then we'll return it. Okay, so in this case there are 10, it is saying 10 square of size 1, then it is saying 4 square of size 2 and 1 square of size 3. If all will add it, it will become 15. Okay, so very first, what the question is saying, that we are given m cross n matrix that is filled with zeros and ones, and we need to count how many square submatrices of all possible size having only consist of ones, right? A square matrix means 1 cross 1, 2 cross 1, like that we have seen, right? So let's talk about the example, right? That example we have given. So very first, if we talk about the in the step 1, let's suppose I'll go with the step 1. Okay, so a step 1, it will count 1 cross 1 squares, right? So if we just count all ones that we have here, there are how many ones are there? 10 ones are there, right? So we'll say, okay, there are 10 ones we have in the given matrix, right? So can we say total how many we can make? The square of size 1, we can make square of size 10 squares of size we can make of size 1 we can make. Okay, then in step 2 we will count 2 cross 2 square. Okay, so if you talk about here, a 2 cross 2 matrix is valid if all cells are 1, all 4 cells are 1, right? So there is possibility if you check here 4 values square will come from here, right? So there, let's suppose we were talking about here, right? So very first will be this, then it will be this, then it will be this, right? Similarly we'll take this one, understand? So means I'm talking about all the 4 cells should contain 1 1 1. Okay, not don't contain this one. Okay, means total if you find it, you will come total size, means all the 4 should contain only 1, right? And for that you will get 4 cells, right? 4 square you will get, sorry, 4 square you will get. How many? 4 square, right? You have to find it from here. Okay, similarly, so 4 here, 10 here. Now for 3 cross 3, step 3 will count for 3 cross 3 square matrix. In the case of 3 cross 3, we have only one from here to here, right? We will say only one is coming. Now you will do plus of all these 3, you will get 15, right? 1 plus 4 plus 10, 15. I hope you understands. So similarly, we have another case we have given in the example 2. I can show you here, but let's suppose we have given 101, then we have 110, and it was 110. This was we have given in example 2. Okay, you can see. So if you form the square of one size, how many are there? 1 2 3 4 5 6. Total are coming 6 from 1 cross 1 for 1 cross 1. Okay, when we talk about 2 cross 2, how many squares we have, right? So for the 2 cross 2, the possibility is that there is only one available for 2 cross 2. So we'll say there is only one cases we have, like for the 2 cross 2 matrices, right? For this one, right? So we'll say okay, there is only one case. Now talk about 3 cross 3. 3 cross 3 is not possible here, so nothing it is coming. All do the sum, you will get 7. Okay, so you have to return 7. I hope you understand the problem, right? Let's understand how to code it. So can I say you understand the problem intuition, right? Very first, let's understand. So if we are going to check every possible square like this, like 1 cross 1, 2 cross 2, 3 cross 3, right? It will be difficult for you, right? And yeah, it's fine, you can write the code and it will work, right? But the problem is that instead of checking every possible square, that is a brute force approach you will try, better you use uh, dp formula, because this is based on the dp, right? So if you apply the brute force approach, right, you know that complexity will get increased because it's 2D matrix, and for each cell it will go, it will give you of nq, right? That will be very slow, right? So better use the dp, dynamic programming. And why dp use? Because you can say it is very slow. Very first that we are going to check for every possible square, right, in the brute force approach, and it will be very slow. So we can use dp, right? And what is the dp formula here? So dp at I and j, for each cell we can say it is nothing but the size of a square ending at cell I and j, right? We can say the size of square ending at cell I and j. Size of the square, size of the largest square, sorry, largest square, right? Ending at cell I and j, right? Means this is the thing we have to define. Then understand if what is the recurrence relation, right? For the recurrence relation, you know the dp, right? So in the recurrence relation, we'll say if matrix at I and j, matrix at I and j, if equal to 1, right? If it is equal to 1, we'll say dp at I and j, we'll say 1 plus, we'll take minimum of dp at I minus 1 will take, and we should take a dp of what, I, yes, and there should be a j minus 1, yes, and one more thing should be there, yeah, dp at corner 1, I think, yes, corner 1, j minus 1, yeah. So all these three that we have seen, right? So dp at I minus 1 and j, we forget, right? This is your left, and this is your top, above, then left, and miss never, and the corner. All the three which is coming from there, we just take 1 plus whatever the maximum we have, right? And in the else condition, we'll say, we'll mark we are not getting anything at that position, maybe it is having 0, we will mark it as a 0. So this is the case we'll say. So very first, why we are doing this, right? Because we know that a square at I and j, right? So at a square at I and j can only be larger as a smaller square, right? That is touching from the you can say top left and top left corner, right? So if the top left was a part of 2 cross 2, let's suppose. So if the top left part was 2 cross 2, so left is what, 3 cross 3, we can say that. And the top is 2 cross 2, then I and j can extend into 3 cross 3 square, and if all are agree, right, so we'll take the minimum of this and we'll say, okay, let's sum up them, and we'll uh, add on to the value, right? And that will be our total number of square. I hope you understand. Let's understand the code. So very first, you define the row, column, right? And this is the result that you have to find the number of word, the square count, right? The count square. And this is your previous, and this is our dp, right? So we'll take a dp 1D array, right? And you can take the 2D array, and then you can also work. So that is your optimized version, we can say, but this is the most optimized version that we are going to use. Very first, you will start from I, 1 to row will go, and then j will go from 1 to column. Very first, we'll check if the matrix, the corner one, is I minus 1, j minus 1 is 1, then we'll find the previous one, right? So we can get the dp at j, and we'll take the minimum of this. So we know that the mean we have is at dp at j minus 1 and dp at this, right? And the previous, that is the combination of these three. Okay, and you will initially you will store the value temp here, and you will swap the value, right? So the swap thing we will do here, right? And we'll update our result. And if not that is case, that is the case, we'll store 0, and finally we'll return result. So this previous you can take here also after this 4, because this is nothing but your top left neighbor, and you can we are taking each time, right? Because we are checking for the dp at I minus 1, j minus 1, right? So we are, what we're doing, we are assigning that value through the temp, right? So we want to save the old dp at j, the top neighbor at here, right, at the temp, right? So whenever we have this previous, right, we will think this is a top left neighbor, right? And we'll store here. Okay, and each time we save the old dp at j, this is our top neighbor, right? And we have everything here, right? As we can see, now we will find the mean, and then we'll add +1, and you will get the dp at j. Okay, and each time we will increase, we'll save, we'll get the count, as you can say, as a type of count, and we'll increase our top. result, and then we'll return the result. But you can ask, what is this dp here, right? Let's suppose you are very beginner. So we'll say dp at j will be the size of the largest square ending at current cell. You can say cell can be cell at I and j, we can say. But since we only need the previous row to calculate the current row, right? So we compress the dp into 1D array of the size column plus 1, right? And so we can say dp at j is nothing but your dp at dp at j is nothing but what I told you, right? We can take the mean of top, we can say the left, and I told you the top left, you can say, right? Or the neighbor, I said the top left neighbor and the top corner, you can say, and you will do the plus. Then we have these variables. We have these variables, you understands what is this, right? So what is this previous? Yeah, so this previous holds the top left neighbor value, right? And we'll say this previous holds the top left neighbors value, right? How we can get from there? We can get from where? We can say dp at I minus 1 and j minus 1, right? When we update dp at j, understand? Do you know the result? Result is the final count of a square, and row and column are the dimension of the matrix. Let's understand the loop structure here. We have created the 2 for loop, right? So basically we iterate over the row, right? And each time we will reset this we want to reset this previous, right? So we are resetting this previous from a new row, right? And we know that we are iterating over the columns, right? So very first you will save the temp, means temp is nothing but we want to save the old dp at j, right? That is a top, right? So very first you store the top here. So we can iterate, because if we update that value, the top value, if we iterate that, means we are not going to check for other values, right? Means very first we have the outer loop that will go row by row, and this is our inner loop will go by the column by column, and each cell at I minus 1 and j minus 1 in the original matrix will update the dp, that you can say, okay? And this is your dp transition, right? So very first we'll check if this value is equal to 1. If the dp matrix, you can say matrix at I minus 1 j minus 1 is 1, means if the current cell is 1, right? So we'll say okay, go with the dp at j minus 1, right? dp at j minus 1 is nothing but what? Left, right? Then dp at j means before we override the store, we will store this value into the temp, right? So dp at j we are going to override here, right? And so this is our top, right? We can say, so we should store somewhere. So we have already stored in the temp, right? Then we'll check the previous is nothing but your top left, right? So we'll get back the value again here, right, through the temp, and then we'll take the minimum of these, right? We'll store this is you will say this is your left, and this is your we can say minimum of left top left, and we'll do +1, and we'll update the value, and finally we'll add the result here, okay? We'll check if the current cell is not 1, it is 0, means no square ends here. So we'll say dp at g is 0, and finally we'll update the similarly, and we'll return the result. Let me know in the comment section that you understood or not. I'll see you in the next one.